Imagine you're asked to find this integral. Can you do that? Well, with what I've taught you so far, no, you can't, because we can't use the power rule because this plus 5 is in the way, and you really don't want to expand this and integrate term by term. So there's a better way for you to do this. This is very similar to the chain rule, and this actually is the chain rule but for integration. So like for derivatives, we're going to introduce a new variable, u. I'm going to let u equal x plus 5. And so we can substitute into our integral. So this becomes u to the 8th dx. Now we have a problem though. We're trying to integrate a u with a dx. Unlike in differentiation, where if they didn't agree, we could just implicitly differentiate, we can't implicitly integrate. We have to have a du in here. What can we do? Let's look at this. Can we use this to get a du? Of course. We can take the derivative with respect to x on both sides. So this gives us du dx equals, this is 1, and this is 0. But we have du dx, not du. So what we can do is multiply by dx on both sides to get du equals dx. And so now I can substitute this here. And now we can integrate. We have, using the power rule for integrals, we have this is 1/9 u to the 9 plus c. And substituting for our u, we have 1/9 x plus 5 to the 9th plus c. This is called integration by substitution. Okay, when solving integration by substitution problems, most people often end up confused when they see something like this, where naturally you would let u equal x plus 5, and so you'd have du dx equals 1 and du equals dx. So they would go and make this substitution, but realize they have x left over, right? I've made a substitution and I have du, but I still have an x. So in this case, what we do is we solve for x in terms of u. U equals x plus 5, so that must mean x equals u minus 5. And we substitute this into here to get, and from here, we can distribute the square roots like this, and then integrate term by term, like this. And then, of course, we can substitute for u in terms of x to get something like this. The second scenario where people get tripped up is when they have too little x. And to show you this, I'm going to let u equal 4 plus x to the 6th. And finding du dx, we have this is 6x to the 5th. And when we solve for du, we have 6x to the 5th dx. But notice, we only have x dx on the numerator. What a lot of people will do here is they'll divide by 6x to the 5th to get dx equals du over 6x to the 5th. And then they'll substitute that in here. They'll end up with this, which is even more confusing than what they started with. So do not do this. Do not solve for dx and then substitute. The only things that you should be doing when trying to make your du appear in the integrand is either just choose a different u or multiply by coefficients. You should never solve for dx like this and substitute in. Integration by substitution, or commonly known as u sub, because u is the most commonly used variable, this can make seemingly impossible integrals seem a lot simpler than they used to be. And the only real way to show that is with more examples. So let's go through some examples. I'm going to do 4 examples for you. 2 indefinite integrals, and then later 2 definite integrals. So let's begin. We're going to find the integral of x squared times square root of x cubed minus 5 dx. So right off the bat, this is probably one of the most complicated things we've done so far. So how can we simplify it? Well, it all begins by choosing a good u. You want to choose a u that gets the most amount of terms into the simplest form possible. Let's try x cubed minus 5. So when we make our substitution, we have integral of x squared square root of u dx. But we have the same problem. We're trying to integrate u with a dx, and even worse, there's still x's in our integrand. So we have to find du, and we do that by differentiating both sides of this with respect to x. And to solve for du, we're going to multiply both sides by dx. Now we have du equals 3x squared dx. But if you look over here, I only have 1x squared dx. So how do we fix this? Well, what we can do is we're going to multiply by 1/3 on the outside of the integral and 3 on the inside of the integral. We can do this because if we pull out the 3, which we can do because integrals are linear operations, that means these will cancel and this integral is the same as this integral. And so I'm going to rearrange this so it looks like, and we know from here that du equals 3x squared dx. So I'm going to substitute that like so. And now look, our integral is a lot more manageable. All right, let's do this integral. So I'm going to rewrite the square root as a fractional power. And then we can go ahead and use a power rule. So we have 1/3 times, so you bump up the exponent by 1 and divide by the new exponent. So dividing by 3/2 is the same as multiplying by 2/3. And then we have a plus c. So simplifying this, we have 2/9 u to the 3/2 plus c. And substituting back for our u, we have 2/9 x cubed minus 5 to the 3/2 plus c. And that's our final answer for the first problem. Okay, time to do the second problem. We're asked to find the integral of tangent squared x, secant squared x, dx. But when you're doing a problem like this, you not only have to consider u, you also have to consider du, because you don't want too many things left over when you do a substitution. Well, I know that the derivative of tangent x is secant squared x, and we already have this here. So let's try u equals tangent x. So this becomes the integral of u squared secant squared x dx. Again, this is a problem. We're trying to integrate u with x and dx. So I'm going to differentiate this on both sides with respect to x. And then I'm going to multiply by dx on both sides, like so. And look, conveniently, we have secant squared x dx. So I'm going to make the substitution, and look at that. This is way simpler than this. And all we have to do now is use the power rule, like so, and substitute back for our u. And this 1/3 tangent cube x plus c is our final answer. All right, for our first definite integral, we have this massive thing with sines, cosines, natural exponential. It's basically got everything. We're going to try our best to simplify it and then evaluate the integral. We start by choosing our u. It would be really hard to do this problem if the exponent wasn't simple. So let's try sine of pi x as our u. So we have this, and as usual, I'm going to differentiate with respect to x on both sides, and then I'm going to multiply by dx on both sides. And look at that. Pi cosine pi x dx. We can make the massive substitution to reduce this to, but we have a problem. These limits are in terms of x. We can either specify that these are in terms of x and evaluate the integral, substitute for x, and then do the definite integral bounds, or we can just change the bounds of integration in terms of u. I'll show you both ways so that you know which one you would prefer and which one you can do when doing problems. We have to evaluate u when x equals pi and when x equals 0. So when x equals pi, so u of pi equals sine of pi squared. And that doesn't simplify to anything, so it's just sine of pi squared. And u of 0 is sine of 0, which is 0. So knowing this can turn into, so this and this are the same thing. This one, you won't get any weird integration limits like sine of pi squared, but the downside is your end computation will probably be a lot more complex, whereas here, you suffer in the beginning by getting these limits, but you never have to substitute for x again. I'll show you both ways. So I'm going to start with this one. So we're going to evaluate, so first off, the integral of e to the u is just e to the u. We're going to evaluate from 0 to sine of pi squared. And this is e to the sine pi squared minus e to the 0, which is e to the sine pi squared minus 1. And this is our final answer for this problem. Now I'll show you this way too. So again, we're going to evaluate e to the u from x equals 0 to x equals pi. But we can't do the definite integral bounds just yet because this is in terms of u, but we are computing in terms of x. So we have to substitute e to the sine of pi x evaluated from, now we can drop the x equals because x is the only variable here, from 0 to pi. And notice that this is e to the sine of pi squared minus e to the 0, which is e to the sine pi squared minus 1, which is exactly the same as what we got here. For our last example, I'm going to evaluate the integral from 0 to 1 of e to the x times 1 plus e to the x to the 11th dx. We really don't want to expand this. Why don't we set this as our u? So this becomes, when we introduce the u, we have to specify that the integral bounds are currently in terms of x, like so. And to find du, we're going to differentiate both sides with respect to x, and then we're going to multiply both sides by dx. Look at that, e to the x dx. So we can substitute, and I'm going to keep specifying there an x and wait until we substitute back in to evaluate. So this is 1/12 u to the 12th evaluated from x equals 0 to x equals 1, which is 1/12 1 plus e to the x to the 12th from 0 to 1. So this is 1/12 1 plus e to the 1 is e to the 12th minus 1/12 1 plus, so e to the 0 is 1 to the 12th. This is 1/12 1 plus e to the 12 minus 1/12 times 2 to the 12. And this is obviously some huge number, so I'm just going to leave it like this. You might have noticed that I've never actually told you how to set u. That's because there's no mathematical formula to find out what u is. It just takes practice with problem solving and some mathematical intuition, which kind of sucks that there's no formula. But to help you, here's some of the 5 most common places that u would work best. There's inside parentheses, inside trig functions, under, square roots, cube roots, stuff like that, inside exponents and under exponents inside parentheses, and really just anything inside another function. You're just looking for composite functions, which you can, substitute that input for u, and hopefully that makes the integral a lot easier.